A very hearty good morning to one and all present on this virtual platform. On behalf of the Department of Chemistry, Bidhan Chandra College, I proudly welcome you to our one-day national webinar, New Horizons of Chemistry, Part 2. In today's webinar, we intend to extend our knowledge about two of the most emerging fields of chemistry, green chemistry and supramolecular chemistry. And our primary intention is to get more acquainted with these developing branches. We also hope that this seminar will enlighten our students in these new arenas of chemistry. Our Honorable Principal, Dr. Falguni Mukhopadhyay, is the patron-in-chief of this webinar. He has indeed been the torch-bearer for all of us and the pillar behind today's program. His inspiration, motivation, and constant supportive endeavor is beyond words. We are really indebted to him. We have with us Dr. Shoman Chatterjee of Chakraborty, IQSC Coordinator, Bidhan Chandra College. I would hereby request him to say a few words and declare the webinar open. Dr. Shoman Chakraborty.
Yes, thank you, Susmita-di. Very good morning to each one of you present today. It is a moment of extreme pleasure to welcome all the guests and participants who are present here to attend as well as interact in this webinar. On behalf of the Bidhan Chandra College, Asansol, I, Dr. Somin Chakraborty, first express my regards to Department of Chemistry for arranging the webinar. I offer my regards to all the people joining us in this webinar. I convey my regards to our eminent speakers, Dr. Ranjan Patro, Associate Professor, Amity Institute of Click Chemistry Research and Studies, Amity University, Noida, and Dr. Pareshnath Chatterjee, Associate Professor, Department of Chemistry, NIT Meghalaya. Thank you, sir, so much, sir, for accepting our invitation and coming over the webinar. This is our second one-day national webinar on New Horizons of Chemistry series, and the topic is based on green and supramolecular chemistry. I have so far no deep knowledge about the topic, but it is one of the most emergent and important topic in the present era. I think the speeches of the speakers who are quite experienced and established in their field enlighten us as well as all the interested delegates over here. It will also enrich our students for their future. The interactive session between all the participants will also enlighten us and make the webinar interesting one. Lastly, I say thank you to everyone whose views and opinion made this conference possible and successful. Thank you.
Thank you, sir. Now, on behalf of the organizing committee, I would like to request all participants to turn off their microphones and their videos so as to enhance the video quality of our speakers. Throughout the presentation, you can put in your questions and views in the comment box, which will be addressed directly after the presentation. With this, we move on to our first technical session. We are indeed honored to have with us today Dr. Ranjan Patro and Dr. Pareshnath. And our first speaker our first resource person will be Dr. Patro. He has completed his master's from the Department of Chemistry and Chemical Technology, Vidyasagar University, and has obtained his PhD degree from Indian Institute of Technology, Kanpur. He carried out his postdoctoral research at Tel Aviv University, Israel, the Johns Hopkins University, USA, and in CFA, France. He was a DST Inspire faculty at Department of Chemistry, Punjab University, Chandigarh, and presently he is working as an associate professor at Amity Institute of Click Chemistry Research and Studies, Noida. In 2019, he had been awarded as Emerging Investigator in Crystal Growth and Design by American Chemical Society. He has also received the International Travel Grant by SERB, Science and Engineering Research Board, New Delhi. With this brief introduction, may I now request Dr. Patro to deliver his talk on supramolecular chemistry, concept and applications. Sir.
Yeah. Thank you, Head of the Department of Chemistry, for giving me the opportunity to present some of the research work which is related to the supramolecular chemistry in my laboratory. Since this lecture is based on all our bachelor's and master student, so I will focus mainly on the technical parts, that how this concept is coming, and then we can able to go for that slowly, that what are the important parameters we should know before we are to understand about the supramolecular chemistry. I hope that you can able to see my slides, and obviously I thank you organizers for giving me this opportunity, as well as the students who are going to listen my talk for a few minutes. And especially thanks to Taponda, because he is my teacher when I am in a bachelor's in my college, Bajkul Milani Mahavidyalaya. He is my teacher, so he giving me invitations. So thank you for that, obviously, because today whatever I have learned also, that is from part of this my experience, whatever I gain from the bachelor's, masters and everywhere. So basically I am going to the supramolecular chemistry. The title of this talk about the supramolecular chemistry concept and its applications. So before going to this lecture, so basically I am in presently I am in Amity University, Noida, and this is the place, this is the campus of this Amity University, Noida. So this is my block where my research laboratory is here, and if you can able to see that our founder president actually have make lot of efforts to make a lot of Amity campuses all over the world. It is in the Amity University New York, Amity University Dubai, Amity University France. Also in India we have a lot of campuses which are conducting that bachelor's, masters and different type of degree. So these are basically in our department. We are basically have the MSc in molecular chemistry. So that is basically we cover up all these recent advances like green chemistry, chemical biology, nanomaterial chemistry in the syllabus, so that the present scenario the student can able to compete with all the world different universities, and they can able to go for the higher studies, particularly after giving the GRE, and they can able to choose for the higher study in different type of different countries. So these are our labs. Basically I am some of these photos I am giving. So these are the some instrumental facilities we have built in our departments by different type of project, by the funded project from the ACRB, CSIR or some other funding agency like DBTs. So now I am coming to that supramolecular chemistry. So when we are telling about the supramolecular chemistry, that this is a chemistry basically the intermolecular bonds. That means it is a molecule. So in a molecule, so if I able to think about a methane molecule, so I can able to see, okay, when we are doing the BSc degree, what is the hybridization of this molecule? So methane, CH4, so it is a sp3 hybridized. Then we can able to know the bond angle. So bond angle is basically 109.28 and like that. We know only about the methane. So that is the molecules. But if I can able to tell about the methane, how it can able to interact with the other molecules, that will deals with the supramolecular chemistry. For example, there are nowadays lot of people are synthesizing lot of molecules, lot of compounds which can able to absorb the methane. Now, how it can able to absorb the methane? Because it can able to interact with the methane molecules by different type of non-covalent interactions, like different type of intermolecular interactions. So that is why that definition of supramolecular chemistry is the chemistry of intermolecular bond. So in methane, we have a sp3 hybridized, as well as we have that CH bond distance as well as the CH bond angles. But these are basically covalent bond, because we know that carbon is sharing with one electrons and hydrogen is sharing with one electron and make a covalent bond, and it will make a sp3 hybridized. So that is basically a covalent bond. But when we are telling about a supramolecular chemistry, we are not telling about a covalent bond, rather than how it can able to interact with the other molecules, that we will discuss in the few minutes of our lectures. So if I able to talk about the supramolecular chemistry, first we have to go for the who are the persons who got the Nobel Prize in supramolecular chemistry. In the past, it is in the Jean-Marie Lane, is basically Pedersen, Lane, and Crumb. In 1987, got the first Nobel Prize about the discovery of crown ether, cryptons, and different type of spherent compound which can able to trap different type of cations like potassium, sodium, and like that. And that cations and anions can able to interact with this potassium ion in that cavity. So basically K plus ion, you know that K plus ion, since it is a basically octet is fill up, so now that there is no electron can able to bond with that oxygen, so that potassium ion can able to interact with the oxygen in supramolecular way, so that that potassium ion can be trapped into the crown ether or different type of cryptons depending on the cavity size of this crown ether or cryptons on that. And this is the first discovery of this basically in the supramolecular chemistry. So but here you have to understand that there is, when I am telling about a potassium, then potassium ion can able to reside into the center of this, and since potassium is already ion is already octet fill up, so it can't able to share the electron with to bond with the oxygen, rather than that oxygen lone pair can able to interact with the potassium ion, and that leads to the trapping of the different type of cations in the crown ether and cryptons. But this is not a bond. When we are telling about a bond, for examples, we have reached in our bachelor's degree that we have different type of bonds: ionic bond, covalent bond, as well as the metallic bond. So here basically ionic bond means, you know that one is cation, another is anion, so they can able to interact with each other. Covalent bond means we have to share the electrons with, I am sharing with one electrons, another atom is sharing with another electrons, and they can able to make the covalent bond. And metallic bond, you know that basically the number of electrons present in the free electron, they can able to fit into the cavity of the whatever the metal have, that creates the metallic bond. But here that is not exactly a bond, because there is no sharing of the electrons, there is no sharing of electrons, there is no transfer of electrons, rather than it is basically a one type of interactions. And that is why they got the first Nobel Prize in 1987. Simultaneously in 2016, here you can see that Savage, Stuttgart, and Feringa got the Nobel Prize due to the invention of the molecular machines. Tiny machines in the molecule can able to act as a machines. So due to this, that is also related to the supramolecular chemistry. So coming to that, about the supramolecular chemistry, about our known concept that when we are I think in the first year we heard about the hydrogen bond, and one of the good example is water molecules. So when we are telling about the hydrogen bond, when we are telling about the intermolecular interaction, first concept will come the hydrogen bond. And that hydrogen bond, if I can able to give a classic example of hydrogen bond, is the water molecules. And we know that how hydrogen bond is created, because this oxygen and hydrogen, due to their electronegativity differences between the two atoms, because this, although this is a covalent bond, hydrogen and oxygen, they are sharing the electrons, but due to the electronegativity difference between the oxygen and hydrogens, so basically due to the more electronegativity nature of oxygen, basically oxygen can able to trap that electrons, the covalent bonded electron towards him. As a result, it will be partially negatively charged, and hydrogen acts as a partially positive charge. And since this is a partially positive and negative charge, so in the other molecules, basically that hydrogen can able to interact with each others, and they can able to make a basically electrostatic force between the oxygen and hydrogens, and that leads to the hydrogen bond interaction in the water molecules. So if I able to tell about the water molecules, it consists of hydrogen bond. How the hydrogen bond is created? That is due to the electronegativity differences between the oxygen and hydrogen. As a result, what will happen? The oxygen is, due to the more electronegativity of this oxygen, the oxygen is basically trapping that electron density towards him. As a result, he is basically partially negatively charged, and hydrogen is partially positively charged. So what will happen when another water molecule will come? So that delta minus is, since it is a negatively charged, so it can able to interact with the delta plus charge. So that is why it is a electrostatic interactions, and that is why it is known as the hydrogen bond. Another classical examples in our body system, for example, is basically, here you can see that DNA structures. So you know that DNA, every human beings, we have a DNA structures, and we have a different type of couples where they are basically able to do the hydrogen bond with different type of amino acids and bases. For example, guanine, cytosine, GC, AT, adenine, thymine. So they can able to make a hydrogen bond interactions, because here you can see that oxygen and hydrogens, due to their electronegativity difference, so this is delta minus and delta plus, so they can able to interact with that, and they can able to make a double helix structures in the DNA structures. So basically, if I call about the hydrogen bond, the one classic example is DNA, another classic example is basically water molecules. So basically that interactions where they are not sharing the electrons, but that is interacting through different electrostatic interactions. So this is known as the basically the supramolecular type interactions. Now, for example, here you can see this is one of the molecules. Here you can see that one of the crown ether type complex. Here you can see in presence of acid, due to the presence of NH group, when this NH group is present, when you are putting, so it is basically protonated. The NH group is protonated. Then this is moving from when you are putting. It will coming to this, because this NH proton can able to hydrogen bond with this oxygen atom present in the crown ether. So this is a molecular shuttle. So when you are putting base, since this nitrogen when you are putting, so base can able to abstract that hydrogen, so there is no people are present in that. So what it will do, to stabilize this hydrogen bond interactions, it will come to these sides. So that molecular shuttle, here you can see this shuttle, this ring can able to go in presence of acid, in presence of base. In presence of acid, it will moving to the towards the amine group. In presence of base, it is moving toward the basically 4,4 dipiryl. So it will make a molecular shuttle, because here you can see due to the when you are putting some acids, so the nitrogen atom is protonated, and what will happen, that oxygen can able to easily hydrogen bond interact through the hydrogen bond, so the shuttle can able to move from this place to this place. Another the examples is basically what we are getting, that basically nowadays you can able to find in, I think everybody have mobiles, you can able to find there's a puzzle game is there. So you can able to do a different type of puzzles, so they can able to in nowadays in market also you can able to find there are different type of puzzles. So that puzzles you have to select a particular key as the lock, because if you can't able to interact with that, then you can't able to fill up the complete puzzle game basically. So you need a key and a lock, and that key and lock must be appropriate with each other, otherwise it will not, you can't able to finish the puzzle game. You can able to download in your mobile, or you can able to purchase a puzzle game through online, but during your game you can able to see there is a one lock, another is a basically key. So if you are not able to connect with each other in proper way, you can't able to finish the puzzle game. In supramolecular interactions also, in DNA also, when we are telling about GC80 guanidine cytosines, but and AT adenine thymine, but we are not telling about the guanidine thiosines. We are not telling, because that proper matching should be there to make the hydrogen bond interactions. So basically, if I able to tell about the different, as I told you that supramolecular chemistry deals with the basically non-covalent interactions, then I have to tell about, that means intermolecular interactions, then I have to tell about what are the different type of intermolecular interaction is present. For example, hydrogen bond is one type of intermolecular interaction, because as I told you that one is delta plus, another is delta minus. So delta plus, delta minus, they are interacting through electrostatically, and they can able to form a hydrogen bond. And you can able to see acetic acid is always present as a dimer, DNA, water molecules, amide linkage, amide-amide bond. So these are all classic hydrogen bonds. Similarly, there are a lot of other interactions. For examples, I can able to give some of the examples in the pi-pi interactions, CH-pi interactions, van der Waals interactions, halogen bonding interaction, and dipole-dipole interactions. So we have a different type of non-covalent interactions. Now, one of the interesting point when we are telling about that, how we know that this is a hydrogen bond interactions, how I can able to know that, or how I can able to know that this is interacting with the other molecules. That means suppose we can able to see the molecules, okay, we have read in our textbook that okay, hydrogen bond interaction is there in acetic acid, because this OH bond is basically can able to hydrogen bond interaction with that. And DNA structure, water molecules, we know that there is a hydrogen bond, but how we know that? So we have to know through their distance and angles. So distance and angle clearly able to tell that whether this atom is interacting with the other atoms or not. For example, for pi-pi stacking, how I can able to know that this is a pi-pi stacking, they are interacting or not, or whether CH-pi interactions, whether pi orbital can able to interact with the hydrogen bond, hydrogen atom or not, how I can able to know that, or any molecules, any hydrogen bond interaction, any interactions, how I can able to know that they are interacting. So ऐसा तो नहीं, how I can able to tell, okay, this molecule is interacting. How you can able to tell that? So there are two important parameters you have to go to. One is the interacting distance, the distance between the who is delta plus and who is delta minus, or I can able to tell one is donor, another is acceptor. So donor and acceptors का जो distance है, the distance between the donor acceptors is one of the important parameters to define whether this is they are two atoms are interacting or not. Whether it is a van der Waals interaction, whether it is a dipole-dipole interaction, whether it is a ion-ion interaction, any type of interactions, the basic thing is that the distance between the two interacting atoms. Number one. Number two, another is angles, because angle is actually also that all angles are not suitable for that. Now question is that what is meant by the distance. So I hope everyone in our bachelor's degree from 10+2 we have heard about the van der Waals radii. So what is that van der Waals definitions? Van der Waals radii. The van der Waals radii is basically that the distance between the center of these two atoms, the center between the two atoms is the distance between the center to center is known as that van der Waals radii. But if you go to the definition, proper definition of the van der Waals radii, what you can able to find that two atoms come closer, still the inter-electronic repulsion can able to start. Two atom come closer, still the inter-electronic repulsions will come. So that is the van der Waals radii. So basically, if I can able to tell the van der Waals radii for fluorine atom is 1.5 angstrom, then two fluorine atom able to come around 1.5 plus 1.5 equal to 3 angstrom. But if I can able to isolate a molecules where I can able to find the distance, observed distance is basically less than 3 angstrom, because according to the van der Waals radii, two atom can't closure, because they can able to come closer, still the inter-electronic repulsion will start. Now they can't able to come closer less than 3 angstrom, because the inter-electronic repulsion will start there. Because as I told you, if I able to tell, for example, the van der Waals radii of fluorine atom is 1.5 angstrom. So two fluorine atom can able to come. So if I can able to tell, it is 3 angstrom, 1.5 plus 1.5 equal to 3 angstrom. But if I able to isolate a molecules and I able to see that the distance between the two interacting atoms are less than 3 angstrom, then I have to tell probably they are interacting, because the distance between the two interacting atoms is less than that of their van der Waals radii. Then I can able to tell yes, they are interacting. Then we have to find what is the reason behind that interaction. Similarly, bond interactions, if I can able to take the and the you can able to find any hydrogen bonded molecules, the observed distance, whatever we are experimentally observed, that is less than that of their sum of the van der Waals radii. That is why we are telling that yes, this oxygen is exactly interacting with the hydrogen atom, and that is why it is a hydrogen bond interaction. So the first concept of supramolecular chemistry is that it is a intermolecular interactions, or intermolecular interaction is created by different non-covalent interactions. When we are telling about the different non-covalent interactions, then we have to think about their van der Waals radii and whether the observed distance is less than that of the van der Waals radii or not. If it is the observed distance is less than that of the van der Waals, less than that of the sum of the van der Waals radii of the two interacting partners, then I can able to tell, yes, there is some interactions. Yes, now we have to get that what is the nature of interaction. That is the next question. First question is that whether they are interacting with each other or not. So the interaction is comes when we can able to get the distance, observed distance is sum of their less than the sum of their van der Waals radii. Then we can able to tell, yes, this is they are interacting. For example, hydrogen bond interactions, if I can able to tell, you can able to find the van der Waals radii of hydrogen and van der Waals radii of oxygen. If you add it, you can able to see their distance is less than that of their sum of the van der Waals radii. Similarly, pi interactions, if you can able to find the radius of the carbon, van der Waals radius of this carbon and another van der Waals radius of this carbon, if you see the distance is less than that of the carbon-carbon distance, then you can able to tell that yes, they are interacting. Now obviously another parameter is angle. How is interacting? The perfect angle for hydrogen bond interaction is 180 degree because it is basically a straight manner. But obviously there are some deviation is depending on the what type of hybridization is present on the molecules or interacting partners, that can able to also detect the angles. But the first point is we have to understand that they are interacting means their observed distance is less than that of their sum of the van der Waals radii. So in water molecules also, in DNA molecules also, or whatever the amino different type of acids, whatever the hydrogen bonding is observed, every cases we can able to see the interacting partner, the distance is the one of the main factors where we can able to tell they are interacting or not. That is the first point you have to keep in mind when we are telling there is some hydrogen bond or there is some interactions, or we are telling about the different type of interaction in supramolecular interactions. So as I told you, I discuss about the basic concept about the different type of hydrogen bond and different type of non-covalent interactions. Now I am coming one of the recent trends of and is known as the halogen bond interactions. Obviously, we can have a questions is that we know in periodic tables that in halogen bond, halogens about that basically fluorine, chlorine, bromine, iodine, and astatine, and we know that they are the most electronegative element along the periods. Basically, if I able to go from the second period, so you can able to see that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So basically, fluorine is the most electronegative element in that halogen family. So similarly, if I able to go for the third period, fourth period, fifth period, we can able to find that fluorine, chlorine, bromine, iodine, they are the most electronegative element in the periodic tables. Then obviously another systematic question is that they are electronegative atoms. Then how they can able to interact, because electronegative means they are taking the electron from the covalent bond. So they are taking the electron, sharing the electron pair from the covalent bond. Then the question arises that how it can, because it is electronegative. So the surface of these atoms is completely negative because it is attracting the electron from the covalent bond. So surface is completely negative. Then how it is possible that a negative can able to interact with the another negative people? It is a impossible task. So that is why it is a question. It is a debatable question. Can halogen can able to interact with the other halogen, or can halogen able to interact with the nitrogen? Interact means, again I am telling, the interact means electrostatically interacting or not, or as I told you, the sum of their van der Waals radii of the two interacting partner is less than that of their sum of the van der Waals radii, the observed distance. Is it possible that two halogen can able to come closer less than that of their van der Waals radii, or one halogen one nitrogen or one oxygen, then they can able to come closer than that of their less than that of their van der Waals radii. It is a debatable question because halogen itself is a electronegative in nature. So electronegative means surface is completely negative. Then how it can able to attract another electronegative people? So it is basically a conceptually, when we are thinking about a halogen bond, I think we have to think about that they are electronegative in nature. They should not interact with a electrophile or with a nucleophile, because they itself is a nucleophile, because their surface is completely negatively charged because of this high electronegativity. So basically what we can able to get that fluorine, chlorine, bromine, iodine and astatine, when we can able to see there are lot of molecules observe, yes, they are interacting with the other partners, other nucleophiles. Nucleophiles means those who have electron pairs. That means Lewis base. Then the question arises, how it is possible that a halogen, he itself is a negatively charged because of their electronegativity. Then how he can able to accept any electron density from the other partners, because other partner can, how he can able to, because itself surface is completely negative, how he can able to interact with the another negative people. So that means if he want to interact with the other negative people, so he have to be positive in somewhere. How it will be positive? I am coming to that question and like that. So it is basically a concept that when we are thinking about a, suppose methyl fluoride or methyl chloride or methyl bromide, so basically one of the electrons is basically sharing with the carbons and it can able to form a sigma bond. Here you can see, I hope you can able to see my cursor. So here you can see during the sigma bond formations, here you can see it can able to share. Halogen have, halogen is the group 17, so one unpaired electron is present, so it can able to share with one electrons, and carbon can able to share with one electron. They can able to covalent bond, so they can able to form a sigma bond. But if
yes, sorry, hello.
Hello.
So I can't see your slide. Are you representing any slide?
Yes, I have.
I think others also facing same problem.
Okay, I am re-sharing again, I think.
For more than 15 minutes actually, it's over.
Oh my God. Oh.
But sir, I can see the slide.
Actually, we are seeing the all slide. Probably network issue or pin issue.
No, network, others things are coming, no?
Please
Can you now see?
Now we can see.
Yeah.
We can see now.
Okay, actually sometimes it's the network issue. So please inform me if you are not able to see the slides. Please.
Thank you. Without slide, it is not.
Yeah, sometimes it's really difficult. Yes.
Okay, thank you. Carry on.
Thank you. So here you can see again, I am telling that when I am telling about any suppose CH3 Cl, CH3 Br, CH3I, when we are telling, so it is a sp3 hybridized, we know. So one of these electron which is present in the group, since halogen one unpaired electron is there, so it can able to share the electron, it will make a covalent bond. So it is a sigma bond is formed. Now if I can able to go for the molecular orbitals, how orbital it look like? So basically along the pz orbitals, one unpaired electron is there, so that is basically sharing with the carbon to make a sigma bond. Then what will happen? This electron density along the pz orbitals is basically shifted towards the carbon because it is here. So along the z axis, or I can able to tell along the CX bond, there is a region where there is a depletion of the electron density, because this electron is already shared. Since one electron is paired, so along the CX bond, what will happen? Along the CX bond, this region is basically created a electron depletion regions where there is a possibility of creating a positive charge on the halogen atoms, and that will create say delta plus charge on the halogens, and that is known as the sigma hole. For examples, I can able to go for the next previous slide again. It is a examples of the methyl fluoride, methyl chloride, methyl bromide, and methyl iodide. Here you can see fluorine highly electronegative. The surface is completely red. When it is a chlorine, here you can see surface is little bit green. When it is a bromine, slow blueness is coming. When it is a iodine, there is a spot is created at the surface of this iodine, and it is a blue in colors, and that is a basically a positive in natures, and that is why it can able to interact with any Lewis base, or you can able to tell any nucleophiles. So again I am telling the halogen bond interactions along the CX bond, there is a creation of the sigma hole at the tip of this carbon, at the tip of these halogens along the CX bond, because of this depletion of the electronic regions. Then due to the delta plus charge created at the surface of this at the surface of this halogen, it can act as a electrophile, or it can act as a Lewis acid. So since it acts as a Lewis acid or it acts as a electrophile, so I can able to use as a catalyst for a Lewis acid catalyzed reactions, or I created a positive hole at the surface of this halogen, so I can use this halogen compound as a Lewis acid catalyzed complex, and like that. So I hope I can able to give a why halogen is created a sigma hole or positive hole at the surface of this halogen. One classic examples I can able to tell. I3 minus, when we are in the bachelor's second year, draw the hybridizations of the I3 minus. So we know that it is a linear structures. So basically when we are telling about that when we are doing the hybridization, so I2 plus I minus we are divided into that, and we have to do the hybridization sp3d. So when we are thinking about rationally, one electronegative atom, how can able to another electronegative atom can able to interact with the other electronegative atoms. So basically there is a sigma hole is created on the halogen atoms, where the I minus can able to give that electron density to that sigma hole, and that is why the I3 minus is formed. Basically I can able to give another classic examples of hydrogen bond versus halogen bond. For examples, 4 chloropphenols. Here you can see it is a 4 chloropphenols. If I able to isolate the structures, what will happen? That the distance that OH, you know the phenol is acidic. So since the electronegative chlorine is there, so this phenol is much more acidic. So they are acidic hydrogen, so they can able to do a strong hydrogen bond interactions. Now when I use the 3,5 dichlorophenols, so here you can see there are two interesting observations I can able to find, that hydrogen bond interaction is present, as well as oxygen is also interacting with the chlorine. Here you can see, because how I can able to know that they are interacting, because the observed distance is less than that of their sum of their van der Waals radii. Then I can able to tell, yes, they are interacting. They are interacting. Now here you can see that during the 4 chlorophenols, the phenolate oxygens are hydrogen bonded and they can able to form a tetramers. But when it is a 3,5 dichlorophenols, this phenolate oxygen can able to do the hydrogen bond as well as the halogen bond with the chlorine atom. Similarly, when you are using the 3,5,6 probably trichloorophenols, here you can see they can able to participate both the halogen bond interaction as well as the hydrogen bond interaction. So basically that is the observations I can able to tell. So the important aspect, if I can able to compare between the two intermolecular interactions, hydrogen bond. So basically the delta plus is created on the hydrogen atoms, and that is why the hydrogen atom acts as a Lewis acid. And if you have nitrogen, oxygen, electronegative atoms or containing lone pairs, so they can able to act as a Lewis base, so they can able to interact with the Lewis acid, Lewis base, they can able to form the hydrogen bond. But in case of the halogen bond, as I told you, that along the CX bond, here you can see there is a creation of the positive hole at the tip of this halogen, or you can able to tell along the CX bond, there is a creation of the positive hole, whereas the surface is negative. Here you can see surface is delta minus, but along the CX bond there is a creation of the delta plus, and this is known as the sigma hole. And since there is a creation of the delta plus, so it acts as a Lewis acid, it acts as a electrophile. So if we can able to give a nucleophile, it will definitely interact with other nucleophile, or it can able to definitely interact with the other Lewis base. So that is the concept of this halogen bond. So here you can see another interesting examples. Here you can see how the halogen, if I can able to put the different type of pyridine derivatives with the iodine, it can able to give a different color complexes, because it can able to do a different type of halogen bond interactions with the iodine molecules, and because of this different type of interaction energy, they can able to create the different type of colors observed in the molecules. So now coming to that as I told you, when we are telling about electrostatic interactions, halogen bond interactions, so there is basically a sigma hole is created at the surface of this halogen, and that is in positive in nature. That is why it acts as a Lewis acid, or it acts as a electrophile. So basically this is the electrostatic surface potential. Here you can see the surface is positive, the blue color indicative is positive. But when we are putting nitrogen, oxygen, here you can see surface is negative, because it is in the it is highly electronegative in nature. So basically, so now you see the first UPAC definitions of this halogen bond is just 8 years before, in 2013, that a halogen bond. So as I told you, it is a controversy that one electronegative atom can't able to interact with the other electronegative atoms. But after analyzing lot of structures, observing their distance, we can able to, at the finally we have the UPAC have come to definitions. No, yes, halogen can able to interact with the other nucleophiles, or halogen can able to interact with the Lewis bases, and they can able to come with the UPAC definition in 2013. Simultaneously, when we are telling, so your next questions when will be there, that what about group 17, what about the group 16, group 15, group 13? Yes, nowadays if you go to the literature, you can able to find chalcogen bonds, nitrogen bonds, tetral bonds. So all are present in the literature, and they are all basically created due to the sigma hole formations at the surface of the halogen or chalcogen or tetral or nitrogens and like that. So these are the things, important points of this. So as I told you, that since halogen creates a sigma hole, it can act as a electrophile, or it can able to attract nucleophiles, or it acts as a Lewis acid. So using that concept, lot of people are using the different research areas, from the anion transport, anion sensing, organocatalysis reactions, and lot of other applications in the area of halogen bond interactions. And you can able to see another interesting observations. You know that thyroids, so particularly girls are facing thyroid problems. because that is why doctors sometimes prescribe that if you have a hyperthyroid, then you don't have to take the iodized salt, you have to take the normal salt rather than non-iodized salt. So in that cases, basically, if I go to the thyroid stimulating hormones, we can able to see that the glycine oxygen and the iodine atom is present, that is basically regulating the hormone, the activity of these hormones, and that is basically responsible for the different type of enzymatic activities. So now obviously next question is that how I can able to tune that how I can able to tune the halogen bond that it can able to interact with that. Obviously my first choice will be iodine or astatine, because when I am going to the down to the group fluorine, chlorine, bromine, iodine, astatine, obviously the electronegativity decreases, size is increases, electron is much more diffused, so you can able to find the sigma hole will be much more. That means the electrophilicity of the astatine will be much more high with respect to the iodine, bromine, chlorine or fluorine. Fluorine is the highest electronegative in nature. So if we down to the group, basically we can able to increase the sigma hole potentials. Since the astatine is electronegative in nature, so we should not expect basically we should not expect that iodine is more in the literature with respect to the astatine because of this radioactivity and like that. So similarly,
Patro, one request.
Yes.
You have to finish another 5 minutes your lecture.
Yes.
We have to maintain time schedule. Please cooperate.
I understand. So basically, I can able to make the different type of electronegative substitution at the periphery, so that it can able to attract much more electrons, or I can able to attach the halogens at the sp carbon atom, because you know sp carbon atom is much more electronegative in nature, so that you can able to get the more electrophilic in nature. So that actually leads that how we can able to modulate the different type of sigma hole, and that leads to the different type of applications in the area of cation anion sensing, in the area of catalysis, in the area of organocatalysis. As I told you, these are acts as a electrophile or acts as a Lewis acid. So there are a lot of people have done on this area that this halogenated compound can act as a Lewis acid catalyte organic transformation reactions. So I am skipping all these things because, as I told you, the time is less. So I am coming one of the two of these examples where I can able to tell that how we can able to utilize that. Here you can see these are the halogenated compound where they can able to utilize for the different type of organocatalysis reactions. So I think my next lecture is the green chemistry. The people are now going to the green chemistry because people are don't want to use the heavy metal for the catalyst. So now the organocatalysis is using for the greener way to think about, because they act as a Lewis acid. So we can able to use as a basically we can able to activate the different bond through Lewis acid characters and perform the different type of organic transformation reactions. So I hope I can able to give a plenty of a small interactions about how I can able to distinguish a halogen bond interactions, and when we are telling a interactions or intermolecular interaction or supramolecular interactions, what we have to keep in mind, that we have to always keep in mind that the interacting partners, interacting distance and the interacting angles, these are the three important parameters when we are telling about the supramolecular interactions. I hope I can able to give a little observations about the intermolecular interactions. So at the end, I must thank Professor Goldberg from Tel Aviv University, late Professor Roth from Johns Hopkins, Professor Latour and Pascal from the University of Nobel, France, and once I am a visiting professor at University of Manchester, UK, with Professor Samuel So I thank them because today whatever I have learned, I get learning from all of them. And finally, I must tell that confidence and hard work is the best medicine to kill the disease called failure. So always think about the positivity, think about your future, think about your higher education, so that we can grow, our society can able to grow, and we can able to convert it into a developed country. So if you have any query in future, you can able to contact me. These are the email address and contact number, and I am happy to give the answers if you have any questions related to that.
Thank
Yes.
you.
Yes.
Thank you, Dr. Patro, for this really informative talk. And I'm sure it will be beneficial for our faculty as well as our students. Now we can have a quick interactive session, and it will be addressed by one of our conveners, Dr. Topon Kumar Shi. Dr. Topon Kumar Shi,
Thank you, Sutupadi. Thank you, Dr. Patro, for giving us a insight of basic chemistry of supramolecular chemistry, basic science behind the chemistry, supramolecular chemistry. Now we can take some question from participants. Please raise your hands, or you can unmute yourself and place your question, if any. Participants, if Sosododda from BB College.
You can able to write in the chat box. If you have any questions, you can able to write in the chat box. I can able to give your answer.
From BB College, Sosododda, Dr. Sosodor Majhi, you raise your hand. If you have any question, please place. From students, if any question, you can place in any language, in your Bengali or English. It is not a problem here.
Yes. If you have any questions, you can ask.
স্টুডেন্টদের পক্ষ থেকে কোনো কোশ্চেন থাকলে
Yes.
Please, Suraj.
Someone is asking questions.
So some uses of supramolecular chemistry.
Yes, in supramolecular in chemistry, you can able to go, as I told you, organocatalysis reaction, sensing reaction, absorption, gas absorption, storage, lot of multiple applications. Nowadays, you can able to tell that DNA, and you can able to replace the hydrogen bond with the some halogen bond through DNA repairing and like that. So basically, there's a lot of applications from the different type of gas storage. You can able to find lot of literatures, because as I told you that when we are making one supramolecular assemblies, then if there is a creation of these cavities, then what will happen is that methane, carbon dioxide, nitrogen dioxide, they can able to trap into that cavity. And since how they can able to trap into that cavity? Because of different type of supramolecular interactions. Like in your molecules, you have different type of hydrogen atoms, you have different type of halogen atoms, so they can able to do the different type of hydrogen bond interactions, pi-pi stacking interactions, halogen bond interactions, or different type of non-covalent interactions, and that is why they are trapped into that cavity, and we can able to use for the different type of gas storage applications. Anion sensing application, as I told you, that since it is created a positive hole, so anion is a negatively charged, so that hole can able to interact with the negatively charged, and it can able to trap that anion. So anion sensing ke liye we can able to apply for that. Even in the catalysis, suppose you have a CO bond, so to make that CO bond is oxygen is lone pairs, so that lone pair can able to interact with the electrophiles or hydrogen bond or a halogen bond, so that the CO bond will be much more weak. So if you give the nucleophile, so that nucleophilic reactions can able to easily done. So there's a lot of areas those people are working in the catalysis, anion sensing, as well as the gas storage, different areas in the supramolecular chemistry.
Thank you, sir.
Any other question? We will take another one question because we have to start our next technical session at 12:10. So if any question, please. So probably no other question is there. So thank you, Dr. Patro, for giving us the opportunity to hear you.
Yeah, thank you very much. Thank you very much for giving me this opportunity. I hope I can.
Now I request our head HOD, Dr. Sutopa Odhikari, please start the next session.
Thank you, Dr. Patro, for the explained talk, and thank you, convener, Dr. Tapun Kumar Shi. We will now move on to our second talk. Our second speaker will highlight on the development and application of green and sustainable chemistry. And to enlighten us, we have Dr. Poreshnath Chatterjee. He did his master's from Rajabaja Science College, University of Calcutta. He then had almost 1 year post-MSc industrial experience in Chembiotic Research International Private Limited. He completed his PhD in the field of organometallics. After almost 1 year of post-PhD teaching experience as Assistant Professor of Chemistry in Techno India, Salt Lake campus, he joined NIT Meghalaya as Assistant Professor of Chemistry in 2013 and currently serving as Associate Professor of the department. So far, he has completed 2 externally sponsored projects by SERB DST and continuing 1 more sponsored project by DST. He has already guided 2 PhD students and published several research articles in journals of international repute. Apart from his academic activities, he is also involved in several student welfare activities. With these few words, may I now request Dr. Chatterjee to deliver his lecture. Sir, please.
Am I audible?
Yes, sir.
All right. Thank you, madam, for your brief introduction. And first and foremost, I would like to thank the organizers of this conference, national webinar, one-day national webinar, and the faculty members of Bidhan Chandra College, Asansol, the principal, the IQAC of the college, and another resource person, Dr. Patro, all the participants, and especially my brother Samim, who actually invited me and gave this platform to share some of our research achievements at NIT Meghalaya. So I hope the screen is visible to all of you, and now I'll make it full screen. Okay, is this screen visible to all of you, the presentation?
Yes, sir. It is visible.
Yes.
All right. Yes, sir. Okay. Okay. So now, without further delay, let me start the presentation. So, first of all, I must thank Dr. Patro for a very beautiful presentation he just made in front of us. Because I do follow papers on supramolecular chemistry, but yeah, because I am not that much expert in that domain, so I had some problem in understanding the detail part. But the way Dr. Patro has presented the very basics, and from the very basic how the advanced application is possible in this area, this has really enlightened me, and I'm also getting a lot of inspiration to read more and more paper on those topics. So now I'll come to my part. So I have given a title something like this: sustainable and greener approaches to organic synthesis, which we try to put in our laboratory at NIT Meghalaya. So I'll just a minute. Okay. So let me first give a little bit introduction about the institute to which I am attached. So National Institute of Technology, this comes under the Institute of National Importance under the Ministry of Education, Government of India. So we have almost one NIT in each state or everywhere in India. So in West Bengal, you will find there is NIT Durgapur or IIST Sibpur. So regarding NIT Meghalaya, we have started our journey in 2012. So we are very young compared to say NIT Durgapur or IIST Shivpur or any other old NITs. And now we are operating from a temporary campus at Shillong, so which is the capital of the state Meghalaya. And the permanent campus is under construction at a place which is very popularly known as Cherrapunji, which is the highest, one of the highest rainfall area in the planet. And recently in NIRF ranking, we had 61st rank among the engineering institutes in 2020. And in our institute, we have 5 engineering departments: computer science, electronics, electrical, mechanical, and civil. And in addition to the 5 engineering departments, we have 3 science department and 1 humanities department. So in these 3 science department, of course, we have physics, chemistry, and mathematics. We offer 4 years BTech program in 5 engineering disciplines and also 2 years MTech program in those departments. And for our science departments, we have 2-year MSc program after BSc, and we normally recruit our students through JAM, followed by a counseling. And in all departments, we offer PhD program. Our capacity in the master's program is 16 till date, and we have started our MSc program since 2015. We have 5 faculties in the department, and we have currently around 20 research scholars who are working under the supervision of different faculties. So this is the outlook, and these are some of the glimpses. These are, let me just put the pointer mode. Yeah. So these are the images of our temporary campus, and this one is the main campus, which is under construction. Now, we have limited resources because we are operating from a temporary campus. We have a lot of constraints, especially the constraint regarding the space. So with that limited resources, we have tried to develop some of the research facilities which our research scholar use, or in many cases our MSc student, they also operates. So we have, these are the facilities we have, like CV, DSC, fluorimeter, spectrophotometer, then UV visible microscopes, and these are the lab. We have a common lab where all the students they work. So this is about the facilities we avail, and we try to do something with these limited resources. Now coming to my research group at NIT Meghalaya, basically my research domain, I can divide it into 3 areas. Basically, I focus on catalysis or developing new methods in the organic chemistry domain. So there I take the help of mostly the catalysis part. So I do catalysis in homogeneous medium. I do catalysis as well as with the heterogeneous medium. So the target is to develop a new method for the organic synthesis. And these are the catalysts, I would say, in my group who does research in my group and contribute to the research area. So this is Mickey. He already got his degree last year. Dipankar already has submitted his thing. I hope by July he will get his degree as well. Gitumuni is also in a very advanced stage of her PhD. So I hope she will be also submitting PhD by December this year. And this is Manik. He's a part-time student. So here I would like to say that we have a sponsored part-time PhD program at NIT Meghalaya, where a person having couple of years of job experience, like teaching in a college or having some R&D experience, and if they do not have PhD, they have the opportunity to do PhD under the sponsored part-time category. So if anybody is interested, they can see our website for more details about this one. And these are the MSc project students who has worked in several times in my group. Many of them are pursuing their higher study, doing PhD. Some of them are doing job. So this is the overall members of my group with whom I try to do something at NIT Meghalaya with the very, very limited resources. Now, as one of the topic of today's discussion is green chemistry, so I thought of starting with the concept of green chemistry. So green chemistry is a very well-known topic nowadays in every curriculum, starting from the BTech program where we normally teach them, engineering chemistry type of topics. There also we try to include green chemistry topics. So nowadays this is very, very important to know the student, or teach the student about the concepts of green chemistry. Now, all of you know that green chemistry has 12 different principles, which I have mentioned here. I will not, of course, go one by one of them, but which are the importance of green chemistry, as Dr. Patro was mentioning, nowadays is very, very demanding. So we have to always think of very good practice. Green chemistry is a good practice, basically, so that we should not harm our environment to do research in the lab. So we have to always think of how we can reduce the harm or the effect on the environment. So there are certain guidelines, 12 guidelines are there. So now what I will try to correlate today, that in our research, how we try to introduce the concept of green chemistry slowly in our research, so that we can create at least some safer chemistry. So that we will try to discuss today. So basically, as I mentioned earlier, that we have few domains in which we work, like homogeneous and heterogeneous catalysis method development. So under that one area which I started at the very beginning of my independent research career at NIT Meghalaya, that is metal or metal oxide promoted organic transformations. So here basically we will be using metal or the metal oxides as a reagent for some organic transformation. For the understanding of the students, all of you are well aware about the Grignard reaction. So Grignard reaction is a reaction where magnesium metal is used for making a carbon-carbon bond. This is the textbook chemistry. So not only magnesium, many other metals are known at their zero oxidation state to show some kind of very excellent organic reactions, like magnesium, bismuth, zinc, indium, tin, etc. They are known to mediate different kinds of especially carbon-carbon bond forming reactions. Now, how these metals are obtained? Most of the cases we directly purchase the metals from the vendors, so they are commercially available. In other case, you can synthesize electrochemically those metals. Or another option is this: you reduce a particular metal salt in situ or ex situ using a suitable reducing agent to their metal in zero oxidation state. So basically, for the last part, which is very popular, because this very concept is used not only to reduce the metal from higher oxidation state to lower oxidation state, people also use this technique to synthesize metal nanoparticles also. So this is a very, very important topic. Now, many reducing agents one can use. Those are reported in literature, like as reducing agents, sometimes alkali metals, like group 1 metals, potassium, sodium, they are used. Hydrogen hydrate, alcohols, sodium hypophosphite, sodium borohydride, sodium citrate, oleamine, ascorbic acid, many things are, I have named some of them. So these reducing agents are very, very commonly used for the reduction of metal salts from higher oxidation state to reduce it to lower oxidation state. Now, one has to understand that you cannot pick up any reducing agent for this reduction purpose. So for that, basically, what is the practice? We need to see the standard reduction potential values for both the reagents, means the reducing agent as well as the metal salt which we want to reduce. So many things, as I mentioned, are known, but one of the reducing agent drew our attention at the very beginning, that is sodium sternite. So basically, one very paper inspired us. During my PhD, I saw one paper from my neighboring lab that they use sodium sternite as the reducing agent to synthesize metal zero. All right. So initially, when we had very limited resources and also chemicals, then I just picked up that reducing agent from the literature and I thought of applying it. So what I did here, in the very first project, what I did here basically, if you see, I just took bismuth chloride. We have taken bismuth chloride salt, and if you add sodium sternite with some bismuth chloride, then immediately it generates bismuth zero, which is a zero oxidation state. And you can see here, this is a very beautiful color change which you can observe. So bismuth chloride is solid, white solid. When you add it in water, it becomes bismuth oxychloride, which is, you can see white suspension is here, and this is the sodium sternite solution, which is colorless. Now if you add these two in the vial, immediately the reaction happens, and you can see the color has changed. So from the distinct color change, you can just find out qualitatively that bismuth 3 plus has been reduced to bismuth 0, and hence this very experiment is used for the qualitative estimation of bismuth 3 plus. If you have bismuth 3 plus in your sample, you can try this one for qualitative estimation. Now, why this induction reaction happens so easily? So that will be clear from this standard reduction potential value, which I mentioned, that to choose a particular reducing agent to reduce a metal salt to its metal zero form, we need to see the reduction potential values. So if you see the reduction potential value of bismuth 3 to bismuth 0, it is plus 0.308 volts, and the same for sternite to sternite is minus 0.93 volts. So from this reduction potential value, we could easily predict that this reduction should happen spontaneously, and that's why this is happening. So after synthesizing this bismuth 0, definitely we have to wash it so that the excess reagent and other things should be removed, and then we isolate the bismuth 0. This bismuth 0 we characterized, although in this case you may not have to characterize because this is a very well established reaction. It's a kind of textbook type of practical, so you may not have to do the characterization, but still we did some basic characterizations like powder XRD and other things just to confirm that this is bismuth 0, because these things are sometimes needed to publish a paper. And then with that bismuth 0, we explored various organic reactions which are mostly carbon-carbon bond forming reactions, and these type of reactions are named as Barbier type reaction. So Barbier type reaction, for the students, it's a very good substitute of Grignard reaction, because Grignard reaction, mostly what you require a very, very sensitive reaction setup. You cannot allow moisture to intervene. So we normally use very, very dry reaction condition for Grignard reaction. But in the Barbier type reaction, you have that liberty to use water as the solvent. So you do not have to be so much careful about the reaction or to making the reaction setup moisture free. So that's the reason we picked up that Barbier type of reaction. And you can see with this bismuth 0, we have executed first the reaction of allyl bromide with aldehydes or imines. Even ketone also you can try with. So basically carbonyls and imines of aldehydes, basically, if you take, so this will be the electrophile, and the allyl bromide reacting with bismuth, they generate kind of nucleophilic reagent. So these two combines and generates this type of homoallyl species. If your X is oxygen, we call it homoallyl alcohol. If your X is having nitrogen species, we call it homoallyl amine. And if you see, the reaction can be done in water solvent. All right. On the other end, the same bismuth can also mediate the propargylation reaction. Here we have taken aldehyde as the electrophile and propargyl bromide as the nucleophilic reagent, means the other reagent, which will generate the nucleophile upon reacting with bismuth. And this reaction also done in water, and you can get homopropargylic alcohol. And the same reaction, same bismuth 0, can also do another type of reaction which is very much similar to the allylation reaction. This is called protylation reaction of the aldehyde. So what you can see here, that bismuth 0 reagent can conceptually they are all look similar, but if you see substrate wide, this is allylation reaction, this is propargylation reaction, and this is protylation reaction. So you can do a lot of reaction with bismuth 0, which is very important in water medium. All right. But here another thing you you must notice what is the amount of bismuth zero we are using. We are not using catalytic amount of bismuth zero. We are using more than stoichiometric amount of the bismuth zero. But what we have done here, after one cycle of reaction, you can choose any reaction, this reaction or this reaction. After one cycle of reaction, what we have noticed, when the reaction gets over, the reaction mixture becomes white in color. Why? Because initially when we have started the reaction with bismuth zero, it is a black color like this. But when the organic reaction gets over, this bismuth zero gets oxidized to bismuth 3, and hence it becomes again whitish. But the advantage is this: you can isolate the inorganic component from here just by centrifugation, and you do the centrifuge and take out the inorganic material. And then what you can do there, if you again reduce it back to bismuth zero by sodium sternite, you can reuse it for another cycle of reaction. So there is, of course, after reduction of the recovered bismuth 3 material, you have that freedom to go for a reusability. So these are the few points which I would like to say. So for this method which we have developed, this is a very user-friendly reaction setup. You don't have to bother about the inert atmosphere. You don't have to bother about moisture-sensitive things. You just take open vessel RB and do the reaction. You do not require any organic solvent. Even you do not require any phase transfer catalyst and any co-reagent. Nothing is needed. You have a huge substrate scope, you can see here, and topmost thing is this: you can reuse the bismuth reagent the way I just mentioned. So now, just to correlate with the concept of green chemistry, you can see we are using a very safer solvent, which is water. So this is one green approach. Bismuth is not that toxic, so you can reuse it. So atom economy is there, reusability is there. So this is how we are trying to at least touch some of the principles of green chemistry in our laboratory. So this work we have already published. Now next, we thought to explore the scope of sternite as reducing agent. So we picked up another metal oxide in higher oxidation state, which is stannous oxide, and we reduced this stannite oxide by sodium sternite. All right, and the stannous oxide gets reduced to tin 0. All right, so this tin 0, again the particle size was very small. I would not say this is nanoparticle, but it was really very small, above 100 nanometers of course, but very small, and that's why it has more surface area. Once you have more surface area, then definitely the reactivity increases. So with this very small particle of tin 0, which we have synthesized from stannous oxide using sodium sternite as the reducing agent, that tin 0 was able to perform the propagylation of aldehyde reaction. It is also a CC coupling reaction. You can see with that you can get homopropagyl alcohol. Now this is a very selective reaction. Why? Because when you take a propagyl bromide and react with an aldehyde, there is a chance of two product formation. One is the homopropagyl alcohol, and other one is the allyl alcohol. But fortunately, in our case, in most of the cases, we got regioselectively we got the homopropagyl alcohol. In 2 occasions only we got small amount of or isolable amount of allyl alcohol, but otherwise in most of the cases we could isolate only the homopropagyl alcohol. That's why we call this is a very regioselective reactions. And here also the amount of tin is almost stoichiometric, a little bit more than stoichiometric, means it is not catalytic. Now why the first reaction, why this reduction reaction happens so easily using sodium sternite, you can understand from the reduction potential value. From tin 2 to tin 0, the reduction potential value is minus 0.1375 volts, whereas for the stannite to stannite, this is minus 0.93 volts. So this is again a feasible reaction, and we got a very good yield of tin 0 in this case, almost more than 90% yield, you can see. So this is the thing, and I would like to mention here again, this reaction also being performed in water at room temperature. So no use of organic solvent. You do not require even heating also. Unlike the previous one, the temperature was 50 degrees centigrade for the reaction with bismuth. Here the reaction happens in room temperature, so no energy requirement is needed, and you can see you have good substrate scope. The reaction is highly chemoselective towards aldehyde. Means if you take aldehyde and a ketone in one pot and add their propargyl bromide and tin in water, then you will find only the aldehyde has reacted, but the ketone will remain unreacted. So if you take a molecule where you have a aldehyde and ketone, both functional groups are present, and if you wish to go for a selective propargylation in the aldehyde functional group, then you can pick up our method. That will be very nice. And not only that, we have also done a lot of mechanistic investigations using NMR study, how the reaction is happening, what is the mechanism. Although I am not telling this thing in detail today, but if you wish to see this thing, you can follow our published paper in Canadian Journal of Chemistry, where we have done an in situ NMR experiment to understand the mechanism of this reaction. Means how this tin is combining with propargyl bromide, what are the species generated, and how that species reacting with the aldehyde. Those things we have investigated in detail by NMR. And also, of course, there were some other control experiments which are mentioned in the paper, that if you wish, you can read it, you will enjoy the paper. Then in the two cases, if I recall the previous case with Bismuth 0 and this tin 0, you notice one thing: the actual metal reagent is used in stoichiometric amount, or little more than that. So I would say one thing, that in terms of green chemistry, here we are basically using a lot of reagent, right? So our intention was to reduce the amount of main metal reagent so that we can make it in a catalytic amount, because catalysis is also a very important part of green chemistry. So the next part, which we basically explored using Sternite, that actually in that work we contributed towards the catalysis part. So what we have done there, basically in that case, we synthesized cuprous oxide nanoparticles using from copper sulfate solution and sodium sternite. So you can notice here, sodium sternite is common in all three works, sodium, because this is the reducing agent, and we have taken here copper sulfate salt. At room temperature, if you mix them, then with time there's a beautiful color change. I have shown it here. Sternite is almost colorless. This is copper sulfate, and if you mix them, immediately after 2 minutes, it first become dark green, then slowly it started becoming yellow and then orange. So after 2 hours, it become fully converted to cuprous oxide. So from this color, one can of course determine that this is cuprous oxide, but you need some more evidences, like you have to go for some other characterization. So we took the help of FEACM, HRTEM, powder XRD, XPS, and so many things, EDX. So with all these characterization techniques, we understood that our synthesized material was cuprous oxide. And I just want to add it here that we have synthesized these cuprous oxide nanoparticles in presence of various stabilizers like CTAB, SDS, PVP, etc. And out of all this, we found that the cuprous oxide, which was synthesized in presence of CTAB, that has very small, its dimension falls under the nanoparticle range, and it gives a very good catalytic activity for a very famous organic reaction that is called 3+2 cycloaddition reaction, or commonly this is known as the click reaction. So you can see this reaction. So first what happens, this alkyl halide RX reacts with the sodium azide. So in this step, basically a simple nucleophilic substitution reaction happens, because from the textbook, the students, you know that azide is a very good nucleophile. So this azide reacts the R group, X is eliminated, you guess the alkyl or aryl azide. So this azide combines with the alkyne in presence of cuprous oxide catalyst, and you get this type of triazoles. Now you notice here we are adding one more thing, unlike the previous two, that is the amount of cuprous oxide. Here the amount of cuprous oxide used is catalytic amount, and here also we did the reaction in water. So you do not require any organic solvent. The reaction happens very nicely in water, and you have also good substrate scope. You can take different kinds of alkyne. Of course, one side, this side should be unsubstituted, and you can take different kinds of alkyl halides for this purpose to get different type of triazoles. And in this case also we have seen one point which was not that much possible in the previous two works, that after completion of one cycle of the reaction you can reuse the cuprous oxide material. But yeah, it is not that good. After the third cycle the yield of this reaction got reduced to 60%, so we thought not of extending the recyclability test, we stopped there. Now, why this reduction happens between copper sulfate and sodium sternite? For that, you can refer to this reduction potential value. Now, this reduction potential value, easily says that this reduction is feasible. But yeah, another possibility is there. Why not your copper 2 is getting reduced to copper 0? All right, so that is also a feasible reaction. We thought we could not eliminate that option. But the thing is this: when we took the XPS, we found that there is evidence of cuprous oxide mostly. So from there we thought, okay, this reduction has been stopped in the copper 1 stage, not to copper 0 stage. So this work also we have published in Journal of Heterocyclic Chemistry. So basically now I do not much explore this topic of using sodium sternite. This was the work of my first PhD student when I just started my research work, having less amount of chemicals and other things. So I stopped this area now. So I now in the same time I moved to another topic, and this happened when another of my junior he joined our institute as Inspire faculty. His name is Mukul. So when Mukul joined in the department as Inspire faculty, so normally he's from the truly nanochemistry background. I am not in that expert in that. I'm just learning day by day. So Mukul used to synthesize different types of nanomaterials. All right. So once in a discussion, I found that he has synthesized a palladium 0 with gamma Fe2O3. Okay, so how this is synthesized? The synthesis technique is very simple. You have to first synthesize Fe3O4 nanoparticles, which is commonly synthesized by a co-precipitation technique, taking a ferric salt and a ferrous salt in highly alkaline medium. And what he has added there, Mukul, that is a modified hydrothermal technique. All right, so in the modified hydrothermal technique, Fe3O4 is synthesized, which is a mixture of Fe2 and Fe3 oxide, and it has a color of black. You can see the color, black color. Now, if you take this Fe3O4 and mix it with palladium 2 salt, such as palladium chloride, and if you put it again under modified hydrothermal condition, then what happens? Basically, the Fe3 present in Fe3O4, Fe3 means Fe3 part of the oxide, that basically reduces the palladium 2 to palladium 0. All right. So after this reduction reaction, what happens? You get palladium and gamma Fe2O3. Now, how it is gamma? It is not alpha or beta. For that, we have done different kinds of basically characterization techniques. From there, we got some assurance that this is gamma Fe2O3. Those things are already addressed in the published paper. But what is interesting, you can see a very discrete color change also, from black to a brown kind of color. All right, and this has palladium 0. And why this reduction is happening? For that, you can refer to again the reduction potential value. All right. So this is the thing. So this catalyst Mukul synthesized for some purposes. So I just took it because the advantage of this composite is this: you have palladium 0 present in it, plus it is magnetic in nature. Means so when I thought there is palladium 0, why not we should explore the very famous Suzuki reaction, Suzuki coupling reaction. So that we did here. We took different types of aryl bromides, and we took different type of boronic acids using that palladium catalyst in presence of sodium hydroxide as base and water as solvent. And of course, at 80 degrees centigrade, we synthesize different types of bis aryl compound. compounds. All right. So in this case, again, you notice we do not require any organic solvent. So again, I just want to repeat that we are trying to improvise some of the principles of green chemistry in our lab. And the advantage of this very catalyst is this: once a cycle is complete, you can easily separate the catalyst just by a external magnet. You can see how easy it is. Suppose in a sample vial, if you have your reaction mixture with the catalyst, you just use the magnet and see all the catalyst is stick to here. All right. So easy separation of catalyst. And on top of that, when you do some reaction with heterogeneous catalyst, the advantage is this: you can reuse the catalyst. It is not only very easy to separate from the reaction mixture, you can reuse the catalyst. So the reusability is mentioned here. Up to 6 cycle, the catalyst has very good efficiency. So this work also we published earlier with Mukul, and this is a very good work. I like this work very much due to the very good concept which Mukul introduced in this work. So apart from this metal or metal oxide promoted organic formations, I have another area of work which is more to the organic chemistry, and that is carbon-carbon bond cleaving reactions. So we try to break carbon-carbon bonds. To make carbon-carbon bonds, so far you have seen all these works I presented, they are more focused on making carbon-carbon bonds. And for the student, I tell you the number of carbon-carbon bond forming reactions are very, very rich in literature. Even in your textbook, you could find so many carbon-carbon bond forming reaction. It could be aldol reaction to Wittig reaction. You can take even Grignard reaction. All are carbon-carbon bond forming reactions. But if I tell you to name some of the carbon-carbon bond breaking reaction, then you have to think a lot, because that is very less explored. There are reasons, because carbon-carbon bonds are very stable thermodynamically, and so it is very easy to form. Whereas to break a carbon-carbon bond, you have to cross so many thermodynamic parameter, statistical parameter, kinetic parameter, and this becomes very challenging. So we took up this project. I will not highlight much on this project. Here in this project, basically, first we initiated our work with a tandem carbon-nitrogen, carbon-carbon bond cleaving reaction. So for that, basically, we are using just ferric chloride as a catalyst, which is very easily available, where I am breaking both carbon-nitrogen bond and carbon-carbon bond. So you have to notice here, to break this carbon-carbon bond, this red color arene should be highly electron-rich and sterically bulky. So you need methoxy in the two ortho positions, and this R group should be at least methyl or methoxy. All right. Then this aromatic ring could be broken out from this system via carbon-carbon bond breaking. We have done a lot of mechanistic investigations as well to understand the events of bond breaking, which bond breaks faster than the other bond. For that, this was some control experiment we executed, where we have established that first the carbon-nitrogen bond cleaves to get this type of intermediate, and later on the carbon-carbon bond cleaves to give you the actual product. So this detailed study is published in Chemistry Select. And later on, we explored this concept to dual CC bond cleaving reaction, where you can see the molecule is similar to the above one, but instead of this nitrogen containing functional group, we have introduced a diketo. Now, I would like to say here, this type of molecules you do not get normally. You have to synthesize this type of molecules. So to synthesize this type of molecules, we developed 2 methods in our lab, which also we have published later on. So coming to this work here also, ferric chloride comes out as a very good catalyst, which is very easily available. And there you can break both the carbon-carbon bond. Although they are carbon-carbon bond by nature, but if you see hybridization wise, they are different. This is carbon sp3, carbon sp3. But if you come here, this is carbon sp3, this is carbon sp2. So based on this difference in hybridization nature, you can break these 2 bonds again in a sequential manner. So those detailed studies we have also done. So we are just exploring these areas. Now, another interesting part, if you notice the previous one, these are all homogeneous catalysis, because ferric chloride we are using in 10%, which basically dissolves in the reaction medium and does the reaction in both cases. Later on, we introduced another heterogeneous catalyst for breaking both carbon-carbon bonds. It is similar to just the previous work which I told, but the catalyst was basically a hyper cross-linked polymer based catalyst. So this catalyst was basically synthesized by my colleague. They actually do work on organic polymers and their applications in various fields. So I just took up their catalyst and I found it has a potential to act as H+ source, so like a Bromide acid. So I took up that, and we were fortunate that this hyper cross-link based heterogeneous catalyst also executed this dual carbon-carbon bond breaking reaction very nicely, and this work also we have done. So when you move from homogeneous catalysis to heterogeneous catalysis, then I must mention here that again you are contributing something more to the green chemistry, because you can reuse the catalyst. Here also we have reused the catalyst for several cycles with very good yield of the reaction. So effectively, if you notice, when you are reusing the catalyst, that means you are using less catalyst loading if you compare. So this is again very, very interesting. So this work we have done in carbon-carbon bond cleavage reaction. And the last one which in this area for carbon-carbon bond breaking, which I want to say, that carbon-carbon bond breaking reaction we also executed in allylic moieties. You can see there's the allylic moiety which is connected to a trimethoxybenzene unit. All right, so students, you can notice that we are all focusing on this part where carbon-carbon bond breaks. It is a very electron-rich arene. So same thing we have chosen and attached to a allylic part, and here also using PTSA. Now from metal catalysts, metal-based catalysts, we came to organic acid as catalysts. So that means again you are using non-metal medium, which is very good in terms of green chemistry. So here PTSA act as a catalyst, and here also you can break this carbon-carbon bond. All right, you can see. So basically, if you notice here, we are breaking a carbon-carbon bond to make another carbon-carbon bond. All right, and there is huge mechanistic investigation associated to this work. We did lot of UV visible experiments. We did lot of NMR experiments to understand that how PTSA, paratoluene sulfonic acid, how it combines with the trimethoxybenzene and activates this one. If you could not activate this arene, then this bond cannot be cleaved. So to understand that mechanism, how H+ coming from PTSA comes and combines with this arene and activate it for breaking this carbon-carbon bond, we fantastically done this one with UV visible and NMR experiments. So these are the 4 topics which I thought of just giving you highlight about the work we have done, and many more is going to come in this carbon-carbon bond cleaving reactions which are going on in our group. Now another part which we focus on, okay, I have a little bit time, so which we focus on is the electrophilic activation of pi activated alcohols. So pi activated alcohol means it could be benzylic alcohol, it could be allylic alcohol, it could be propargylic alcohol. So we are not focused on benzylic and allylic alcohol. I have focused on basically the propargylic alcohols, to apply propargylic alcohol as electrophile and to apply it for different kinds of carbocycle formation or heterocycle formation. So this is again a well established area, but for the students I would like to say that the propargylic alcohol looks like this. When you introduce propargylic alcohol with any Bromide acid or Lewis acid, so it can form a propargylic carbocation. The propargylic carbocation, due to this triple bond present in it, can go for a resonance to give you allynyl carbocation. All right. So due to the resonance, either it can show reactivity from propargylic carbocation point of view, or it can show reactivity from allynyl carbocation point of view. All right. So this is basically ambident electrophile. This acts as an ambident electrophile. Now, if you have bulky R and R prime, then nucleophile normally does not prefer to attack here. They will try to attack in the less crowded acetylenic position, which is this. But if you have R and R prime which are sterically smaller, like hydrogen, or one hydrogen, other one as a arene or a methyl, then we have noticed that the nucleophile prefers to attack here. All right. So keeping that concept in mind, what we have done, we have taken different kinds of tertiary propargylic alcohols. Tertiary means this center should be fully substituted. R prime should be either a alkyl or aryl. R double prime should be alkyl or aryl. All right. Plus there should be one aromatic ring which is connected to the triple bond of the propargylic alcohol. So we call it as a tertiary propargylic alcohol. So if you take this type of tertiary propargylic alcohols and react with electron-rich and sterically bulky arene, because I mentioned if you take a very bulky nucleophile, then preferably the bulky nucleophile will prefer to attack in the less crowded acetylenic position, which can give you a different kind of chemistry. So that's the reason we have chosen electron-rich and sterically bulky arenes and heteroarenes, and we have used organocatalyst, PTSA, para-toluene sulfonic acid, and in that case basically we achieved indene as the product. Indene is a very important carbocycle. It has a lot of importances which I am not mentioning here. But what will happen if you do not take electron-rich and sterically bulky arenes? So for that, we have noticed when we are taking electron-rich, but they are not that much sterically bulky compared to the arenes or heteroarenes which gave the indene product, then we notice that in this case, you can see you have taken a propargylic alcohol, we are taking some arenes, but we are not getting any indene like this. What we are getting, we are not getting an indene, rather we are getting a rearranged ketone. So when you get this rearranged ketone, there is no business of these arenes. This rearranged ketone directly comes from this alcohol. So this is another thing. This is again a name reaction. This rearrangement has called as Mayer-Schuster rearrangement. So when you have not taken a sufficient nucleophilic reagent, then what may happen? A parallel reaction may form, which gives you this type of rearranged ketone instead of your desired indene product. So when we did all these control studies, we also noticed once you take 1,3-dimethoxybenzene and a propargylic alcohol in your condition, then you get only allyl. This allyl never moves to the indene. So when we got this one, we thought allyl could be the intermediate in our case. So let's try to isolate the allyl intermediate so that we will understand the mechanism in much better sense. So for that, what we have done, we have taken a propargylic alcohol, tertiary of course. We took 1,3,5-trimethoxybenzene, which is electron-rich plus sterically bulky arene, and of course our catalyst we took. So in this condition at room temperature, what we found, we isolated the allyl intermediate. Then this allyl intermediate we exposed to two different reaction conditions, one with the catalyst, other one without the catalyst, but you can see solvent temperature are same in both cases. So where we have used the catalyst PTSA, there we could convert this allyl to the desired indene, but where we have not used any catalyst, there the allyl remain unreacted. All right, so this is how we got the idea of how the reaction is proceeding via an allyl intermediate. But people may ask you, how do you know that this is allyl and this is your indene? Because if you see the molecular formula, they are same. If you see the molecular weight, they are same. All right, so how do you understand that this is allyl has been formed and you are getting later on an indene? So for that, basically it is very simple. You can understand this by NMR. If you just compare the proton NMR of allyl and indene and 13C similarly, you can easily understand, because one thing in the allyl, all right, in the allyl you can see in this part there is no proton, around 6.5, but when you have the indene, a proton comes just after 6.5, which is highlighted here, and this proton is due to this hydrogen. All right, so this singlet appears number 1 in the indene, which is not available in the allyl. And similarly in the allyl, if you record 13C NMR, this allynic carbon, middle carbon, which I am highlighting, that all of you know that comes around 200 ppm in 13C, which is very clearly visible in the 13C NMR of the allyl. And surprisingly, you can see, and not surprisingly, quite expectedly in the indene, this is not available. So from proton and 13C, you can easily distinguish between the allyl and the indene. So after getting all this insight that the substrate, they form an intermediate allyl, and subsequently that allyl gets converted to the your final product indene, then we proposed a mechanism. The proposed reaction mechanism will be something like this, that first your propargylic alcohol will be protonated at the OH group, all right, and then arene reacts at the less crowded position, and then it gives an allyl. This allyl basically gives you the indene. Now we got two types of indene. If your aromatic ring, what you have taken, if the ortho positions are blocked of this arene, then this aromatic ring takes part in the cyclization. You will get this type of indenes. But if you take an arene whose ortho position is free, but this is electron rich, then these two competes. And what happens, the arene, this red color arene, which is electron rich compared to this aromatic ring, and ortho position is free here, so this arene now takes part, which happens when you take 1, 2, 3 trimethoxybenzene here. If you see, in that case, this arene cyclize this and give you another indene. So this is how we proposed the reaction mechanism. So after getting this concept, this is the motivation. You can see previous work that propagylic alcohol reacts with trimethoxybenzene, gives an allyl intermediate, further it goes to indene. So this was the motivation. So we thought, instead of taking 1,3,5 trimethoxybenzene, if I take 1,3,5 trihydroxybenzene, which is called as fluorogucinol. If you take fluorogucinol, then what we thought, that if you take fluorogucinol instead of 1,3,5 trimethoxybenzene, then allyl should form, and afterwards what happened, this phenolic OH should take part or may take part to form a benzopyran. So encouraged by this one, actually we developed a process of synthesizing different kinds of benzopyrans, and those benzopyrans were we studied with some biological property, which I'll come later. Now this reaction, basically this particular reaction we explored in a heterogeneous reaction medium using a heterogeneous catalyst. If you recall, I have mentioned about this catalyst previously. This catalyst is basically a catalyst which is hyper cross-link based polymer. All right, so how this is synthesized? For that you have to take this type of tetraphenyl substituted ethylene. You just go for a Friedel cap alkylation reaction and you will get this type of hyper cross-link polymer. And in the aromatic ring, you can easily introduce the sulfonic acid group. We call it sulfonation reaction using chlorosulfonic acid, and you can add lot of sulfonic acid. So what happens with polymer is now getting lot of sulfonic acid, and now it can act as a very good source of H+. So we have used this catalyst. This is an organic polymer. Now you can see with that catalyst, basically we have executed our plan, and you can see we have synthesized different types of benzopyran derivatives. As this catalyst is heterogeneous, so we could also try it for using multiple times. So we have seen up to 4th cycle, it has more than 60% yield. So this is also additionally a very good point in terms of green chemistry. And this is a metal free, so means you are basically polluting the environment less, and for that you do not require any inert atmosphere. It's a recyclable catalyst. And the proposed mechanism will look like this, that your propagylic alcohol will interact with H+ to get propagylic carbocation, and then further it will go to allynyl carbocation, and now your bulky arene will attack in the less crowded acetylenedic position to give an allyl intermediate. Now in this allyl intermediate, it will be protonated, followed by attack by the OH group in this position to give the benzopyran. So this is the proposed mechanism. And these benzopyrans, we, as I mentioned earlier, we have studied some of the biophysical properties. So here I am just giving a little bit highlight about what we have done. There are huge study here also. I am not exploring that. So we took all the benzopyrans we have synthesized in our technique, and we saw the binding study with human serum albumin. So it's a protein basically. So this protein ligand interaction we have studied. So basically for this part, again, my colleague there, Otonu, he's also junior to me during my PhD. So he looks after this area exclusively. He is expert in that. So we just synthesize these molecules, give it to Otonu, and his group works on that. So for 4 molecules, we got some, fluorescence quenching studies we have done. Many more are going on. Interpretation is going on. Some good results are also coming out. And also we are trying to correlate these results with molecular docking study. So this part is exclusively taken care of by Otonu. So we are drafting this paper and hope we will submit it soon. So this is all about some glimpse about what I try to do at NIT Meghalaya and with limited resources. So at the end, I have almost reached at the end of my presentation. So I would like to acknowledge ACRB, DST, TechEve3 for funding and of course NIT Meghalaya, to whatever resources we get through NIT Meghalaya only. And we do not have any, of course, we do not have any analytical facilities. You have seen already, like in MR, mass, we do not have. And if you notice my work, we have to do a lot of analysis with sophisticated instruments that I do normally from other institutes like NEHU, Northeastern Hill University, which is very near to our institute, IIT Guwahati, IIT Roorkee. Even sometime I also do tests from IIT Kharagpur, Bombay, wherever is possible. And for that regard, I must acknowledge some of my very good seniors who always help me and encourage me whatever I could achieve. I name some of them: Devuda, Subhasda, Joyantoda, and my junior come friend Arunabho, Atanu, Pradip Da, and all these people. They are really helpful to me. Otherwise, it's very difficult for me to do something there. Shogoto, Arun, these two people, Mukul, Shogoto, Arun, these three are always enrich me with the knowledge of nanochemistry. They are very expert in that. So whatever nano related or metal based agent first work I did, they have always enriched me with their knowledge. And of course, at the end, I would like to thank the organizers, the principal of Bidhan Chandra College, for encouraging the department to organize such event. IQAC, the chairman of IQAC, for supporting the department, all the participants from different colleges and the student, of course. I thank all of you for your patience, and my another colleague who is presented today as resource person, Dr. Ranjan Patro, and lastly Samim. Thank you, Bhai, for inviting me to present some of our research work in front of a very nice audience. At the end, I will say, stay home, stay safe, and try to follow the COVID protocols and read a lot of chemistry. Thank you so much. Now I'll be happy to answer your queries.
Thank you, sir, for enlightening us. The session is now open for questions, and the session will be addressed by our other convener, Dr. Shamim Akhtar.
Thank you, Shrutabadi. Okay, now the session is open to all for question answers. Participants, if you have any queries, please raise your hand or write in the chat box. Participants, if you have any queries, you can write in the chat box or raise your hand.
Or if you wish, you can
ask the question directly to Professor.
Yeah, or for the students or anyone, if you have any queries come later also, like Dr. Patro said, you can collect my email ID from Samim, and you can email me as well. For any kind of chemistry related discussions, anything related to chemistry, you can of course contact me.
I think
if there are no more questions, then we must thank Professor Pareshnath Chatterjee for his excellent and insightful talk. I would now ask our HOD madam to go for the next segment of the webinar.
Thank you all. And I know we all are all hungry. Without further ado, I would like to thank our speakers, Dr. Ranjan Patro and Dr. Pareshnath Chatterjee, for enlightening us with their informative lectures. Today's webinar gave a deep insight into the topics and revealed some interesting facts. Thank you so much. A special thanks to our principal, Dr. Falguni Mukhopadhyay, for giving the permission to organize this webinar and for providing immense support to make it successful. We are also thankful to governing body of Bidhan Chandra College, Asansol, and all faculty members of this college. I would like to take this opportunity to thank the faculty members of different institutes, research scholars, and our beloved students who participated and made this webinar a grand success. A special thanks to the conveners, Dr. Topon Kumar Shi and Dr. Samim Akhtar, and the entire Department of Chemistry for their help and support. Once again, I would like to thank you all, and all participants are just requested to fill in the feedback form and send the email to the email IDs given, and so that we can supply you with the certificates. Once again, thank you all. Stay home, stay safe. And so with this, we end our webinar today, one-day webinar today.
Ma'am, can I ask one question?
Yes, of course.
From where we get the feedback form?
It is being given in the chat box, I suppose. The
No,
feedback
actually,
form.
I got disconnected, so there is no message in chat box.
Okay, it will be sent to your mail ID.
Okay, thank you.
The email IDs, the ones you all have joined with, that the feedback form will be sent to the email ID given. It is there in the chat box, and if you had been disconnected, it will be sent to your email ID. Once again, I thank you all for your cooperation. Thank you. Stop.